idea that what is maths based upon.
Mhm.
And then you also told us that you focused on that question during your undergraduate years. So, I mean, if I look at science, I mean, there are some fundamentals that you can observe and you can build upon those fundamentals. But
Right.
how do we establish fundamentals in mathematics? And I mean, what was the conclusion that you came up with after thinking about that question?
I think if I give you the answer, uh, I will be robbing you of a very important journey that you need to take yourself. Um, because I want you to have a similar journey, or perhaps even a better journey, because going through these questions is important. And let me also just add in an important comment that I hoped to make in the last session, which is in mathematics, your questions are equally as important as your answers, and perhaps even more important than the answers, because asking good questions and then having the patience to and having the creativity to ask questions that lead you to insightful answers, I think that's the trait that most um, mathematicians have had who've had any sort of impact in the field. They've been really creative and they've asked the right questions and have gone in search of answering the right question. So I'm not going to tell you what I came up with, but I think it's not that I came up with anything, but I basically read on the ideas of formal how do you formalize each and every mathematical statement? How do you make precise each and every statement that you make? And how do you boil down? So if you want to make the simplest claim, which is 1 + 1 = 2, how do you boil that down to the bare bones um, that you can construct? And then suppose once you have that system, what do you expect from that system? If suppose I ended up creating let's suppose this, I wrote a book and I say, starting from the first page, you will get a few axioms and then everything else follows from the axioms. By the way, great book. Hopefully you'll read this at some point. But so suppose you follow the rules of inferences and I tell you that let's suppose this one volume contains the entire mathematical knowledge of so far, whatever we've discovered or invented so far. And of course, that volume would be much, much larger than this. But if I were to give you that whole structure, the whole system, then the important questions that were asked were, what do you expect from this system? Well, you expect that if I give you, let's say, well, I of course won't be able to give you a book. Let's say I give you, um, a billion hard drives full of data that contain all of your mathematical knowledge. And I make the ambitious claim that every possible mathematical fact is within that in database that I've just given you. You're rightly going to be skeptical about that claim. You're first going to wonder, well, how many mathematical statements are there? And if my knowledge base contains all the possible theorems really, and if it does it contain statements that may not uh, be true? Perhaps some inconsistency has seeped in, perhaps there's some contradiction somewhere, and perhaps I've made a mistake. So there are several things that can go wrong in such an enterprise, right? So is my system sort of consistent? Is it free of any mistakes? Is my system uh, complete in that it contains all of the mathematical facts that you can think of? And if I've proved everything logically, so we'll talk about proofs today, and you'll see how we prove things in mathematics. So there's a lot that can be asked about when you go and search for that few basic rules, well, few basic axioms, and then build upon them using some logical rules, right? So there's a lot to unpack there. So if you want to look into that, you will end up reading about the works of Hilbert, and of eventually you will come to Gödel's incompleteness theorems, and that's a wonderful journey which I am not going to rock you off, and I can't even expound on that in a few minutes anyway. But it's a great question, and I would encourage you to read up on it as much as possible, and I can give you a few guidelines on where to look into it. Yeah, I hope that answers the question.
May I say something?
Yeah.
Okay, so I was just watching your last session, like the day before yesterday's one, and there you were, like we were discussing, you were discussing what is mathematics for you. So I mean, for some reason, I always think that mathematics is a language of nature. It is a language of God, as Galileo said himself, that it is a language in which God has spoken, or it's like told you about the universe. So what is your opinion about that? How do you see maths as a language of God?
Okay. So I don't have religious, strong religious beliefs, which I can, so it's people do, and that it makes perfect sense, because mathematics is it's a language that we understand, and it's a language that the world seems to be working in, and the world seems to be following the exact sort of rules that we've sort of come up with. And our best sort of understanding of the world is incomplete if we don't employ mathematics, right? So if so, as far as I'm concerned, it's a good question, in that I've not thought of this question for myself for a long time. But mathematics to me is it seems to be the one discipline that sort of makes sense, right? I think the idea is still appealing to me, in that you solve problems using ideas, and it's the whole enterprise contains of asking interesting questions, and then this amazing thing that happens is when you are seemingly solving problems that you randomly came up with, or somebody was bored and came up with a problem, and then you solved it, and somehow it ended up being applicable in the real world somehow. And it seems to me, I think, an essential, it seems to me the pinnacle of what the human mind is capable of. And I think it is the best chance that we have in understanding what really is nature, right? And I do strongly believe that our best understanding of nature comes from mathematics, right? So take the current best theories of particle physics, or take the current best theories of gravitation. So rather it be on the macro scale or on the micro scale, we still don't have a theory that combines our best two theories in those two scales. But even then, the best tool that we have or the best theory we have has come up from the best tool that we have, which is mathematics, right? So developing an understanding which is that accurate. And when I say our best understanding, I mean a theory that we come up with, which is testifiable in nature, which you can test. If you have a theory about the world, you need to make some predictions about the world, and those predictions need to match with what you observe in the real world. So if you tell me that the world works a certain way, and then you say, I predict this will happen tomorrow, and I wait for tomorrow and that thing doesn't happen, I'm going to say your theory is garbage, right? So our best theories are very much rooted in mathematical constructs. So for me, it seems to me the best sort of tool that we have. Now, I'm myself undecided on the question of whether it's discovered or whether it's invented. My understanding would be that it's because we are not detached from nature, we are ourselves part of nature, then it doesn't seem outrageous that we sort of were able to understand the same rules that we're ourselves governed with, right? So it's an interesting idea that, you know, the universe sort of discovering itself through us, which is because we're part of the universe. So it's yeah, I don't know if that answers the question, but that's what I think about when I think about that.
First of all, it was not a question. It was just like, it is just a statement which I wanted your views on. So if you just allow me to, so I can share just one view related to this ideology, and that is the concept of infinity, which we were discussing day before yesterday as well. So regardless of how close you are, I mean, the biggest number you can think of, you are so far from that concept of infinity. Infinity is something you cannot even imagine. It is not in your mind. You cannot bring it into your mind. So that is something you can relate it to. So how as far as you can go, and you think that you've understood the nature or you've understood God, it is quite far from you. So that is one thing, which I can relate, that yes, mathematics is something which will make you understand, which will help you understand how God works or how the nature works.
Right. I have views on this which I will not share because there's a good chance that this might turn into a religious discussion, which I want to keep strictly mathematical. So let's. But the point that you raised about infinity is quite interesting, because this, again, infinity is a concept. Now, I'm not sure if I agree with the statement that you made that you can't bring infinity into your head, because you will see in the fourth week when we start talking about calculus, is that the entire discipline of calculus sort of actually depends upon us making use of this elusive idea. So I'm not going to comment much on this. We'll come back to infinity, and maybe we might get the chance to talk about a little bit of infinity today. But we have gotten a better sense of the idea or the concept of infinity, and we've put it to use. We've gotten some really good insights out of it. So without further ado, I'll just go back. If there are any further comments, we can talk about it after the class or on Discord. But I think let's just talk about what I wanted to talk about today, which is some sort of proofs. And I'll get into it. But before I get into it, I want to come back to this idea of the square root of 2. And so we saw that this square root of 2 is sort of an elusive idea so far, because, well, the only thing that we've been able to say about the square root of 2 is it seems like it should exist. And the reason it seems like it should exist stems from our understanding of the Pythagoras theorem. And because I can construct this triangle, this right angle triangle, whose length I'm sure is, if that length exists, then that length is the square root of 2. And so it now is a very compelling idea to me that the square root of 2 should be a number, but I want to get a feel of it, right? With this, when I just take 2 and put a symbol on it, it doesn't give me a feel for the number. The numbers that I have so far are something like this. The numbers that I have are 0, 1, 2, 3. And I could put numbers between them, which are 0.1, 0.2, 0.3, 1.1, 1.2, and so on. And I could put numbers between them as well, which are 0.01, 0.02. And you've done this, of course, and you can sort of go into the depth of these numbers. Now, these numbers are, of course, all rational numbers so far. Can anyone help me say why these are rational numbers?
They can be written as the ratio of two integers.
So could you pick out just one number and give me an example of how it can be written as a ratio of two integers?
0.1 equals to 1 over 10.
Right, so this is the same as 1 over 10, and this is the same as 2 over 100. And sorry about that. Okay, so these are all, so far, these are rational numbers, and the nice representation that we've come up with is the real number line, which looks something like this. We put a 0 here and we say, okay, we make these two arrows suggesting that these numbers keep going on, and at equal intervals we place 1, 2, 3, 4, 5, and so on, and there's a -1 and a -2 and so on. So I've put on the integers there, and I can of course put down any number that I can think of somewhere between them. So now and as far as, let me just make one more comment about these reals, is that there's sort of two levels of infinity that are going in this representation. When you make this representation, there's two levels of infinity. The first level of infinity is denoted by these arrows going in opposite directions. This arrow indicates that positive numbers keep on increasing and you can keep thinking of bigger and bigger numbers. And this arrow indicates that negative numbers will also keep going on and you can think of more negative numbers, right? So let me say smaller and smaller numbers, or rather bigger and bigger numbers with a negative sign. So that's the first level of infinity. The other level of infinity is actually hidden in every part of this line that I've just drawn. Because notice that if I just take out this part right here, okay, I just zoom into it a little bit, and I zoom into it and I draw it like this. I put a 0 here and I put a 1 here, and I've just zoomed into it, and I can now put a 0.5 here, or if you don't want to do the decimal representation, you can just do the rational representation, which is 1/2. Now, I've sort of zoomed into it once, but I can zoom into it as many times as I want, and there's no point that I will run out of, it's not like that I zoom into this this mouse here and I zoom into it as much as I want. At some point, I'll start seeing the molecules that make up this structure, right? This plastic material. Now, of course, an argument can be made that you can still go deeper and deeper, but the idea is that you won't see the smooth surface once you hit a particular level. You'll start seeing the molecules, but this line remains a line regardless of how much you zoom into it. So if I now want to zoom into this part of this line, this is 0, this is 0.5, and now I still have a 0.25 here. And again, I can repeat this exercise. The other level of infinity that I was talking about is that this is sort of like an infinitely stretchable rubber band, or an infinitely stretchable fabric, if you want to think of it, just one line of it. Of course, if you go into 2 dimensions, then that fabric analogy works better. But for 1 dimension, I think a rubber band is the most, but you can stretch that rubber band as much as you want, and it's not going to break, and it's not going to, you're not going to start seeing the particles at any point. So that's the second level of infinity that's sort of built into this set of real numbers, which we sort of have named, but we also, by the way, don't have a good understanding of it yet, at least from what we've talked about. Okay. Is everyone clear on this? Any questions? Any comments?
No.
Okay. All right, so that was the second level of infinity. So now I want to know, if I name this number as square root 2, where are you going to put that number? on this long line, where would you put this number?
Between 1 and 2.
So on
Why
which
would you do
level?
that?
On which level of infinity would you want us to place a number?
Well, let's suppose I'm still on this
Like how
level, right?
precise?
Let's the first level.
Between 1 and
Just
2 then.
one between 1 and 2. Okay, so you want to place it somewhere here, but so somebody needs to mute themselves. Thank you. Okay, yeah. So why between 1 and 2? Can somebody give me a reason for it?
The square root of 2 is between the square root of 4 and the square root of 1,
One, yeah.
which is 1
Okay.
and 2 respectively.
Right. So the square of the square of 1 is 1, and the square of 2 is 4. Now, if I'm looking for a number which is x squared equals 2, then of course it's going to be between 1 and 2. At least that's what our intuition says. So it's going to be somewhere here, because when I square this number, it stays right here. When I square this number, it jumps here. Now, if I were to take a number bigger than 2, it's going to jump farther than 4. And if I were to take a number smaller than 1, then you can try it out. It's going to stay behind 1. So if I want a number that sort of jumps to 2 when I square it, the only hope that I have of finding that number is somewhere between between these two numbers. So it's somewhere here. And now, so I have a possible region for finding the square root of 2. Okay, can I make a better estimate for this? Can you tell me how can I make the region that I'm looking for this number in? So it's somewhere here. Can I make this even smaller?
It's between 1 and 1.5.
Okay, so let's say I further divide this number between 1 and 1.5. Now I can ask the question whether it's here or here. And Rhyme, how did you decide that it was between 1 and 1.5? How did you
1.5 squared is 2.25.
sorry, 1.5 squared is what?
2.25.
2.25. That means the square of this number is already bigger than 2. I'm looking for a number whose square is 2 itself. So that means I've sort of decided that it can't be here. It has to be somewhere here. Okay, so I've shortened it further. Can I continue this process? So now let's zoom into this level, and I have 1 and 1.5. Now, how can I make this region smaller?
It'll be between 1.4 and 1.45.
Between 1.4 and 1.45. How did you come up with that?
Because if you take out the square of 1.4, that would be what? Maybe 1.96.
So 1.4 squared gives you something less than 2?
Yeah, less than 2, very closer to 2. So that is 1.96.
Okay, so what you've done is a much faster version of, zooming into the right level. What I was doing at every level was I was just dividing it by 2 and checking out the middle point, right? So what I would have done at this point, I would have just done 1.25. So what I was doing was actually something called bisection search, right? Or bisection, you can call it the bisection method of finding a root. I was just bisecting the region and trying to figure out, is it in the left one or is it in the right one? And you can check by just checking the middle number. What you did was you just checked some other number, which was 1.4, and you immediately got an even smaller number. Now you can, of course, carry out this process and make it as small as possible. So between 1.4 and 1.45, you have this region. you can now zoom into it and you can get a smaller region. So I have some sense of it. So it's starting to get some shape. I'm starting to see that it's maybe 1.4 something, and maybe if I keep doing this, I can get more and more decimal numbers, and I can start convincing myself that, you know what, actually this does look like one of the numbers that we've already been dealing with, right? So we have a better sense of square root of 2. It's 1.4 something, right? But here's where the story gets interesting, which is it's unlike any of the numbers that we've seen so far. The numbers that we've seen so far are nice numbers, which are rational and which can be written as P over Q. We define them as, we can write them as P over Q, where P and Q are both integers and Q is a non-zero integer. Okay. And now the question is, of course, it looks like if it were just, if square root 2, and this is absolutely false, but if square root of 2 was 1.4, I could write it as 14 over 10. Yeah.
Yes, sir.
That would make it a rational number. But it's not, of course, equals to 1.4. But maybe if it's equals to, let's say, 1.41, then I could write it as 141 over 100. Then again, it's a rational number. But of course, it's not. You can find another decimal number. Let's say it was 1.41, I don't know, 2. Then it was 1412 divided by 1,000, and I could still get a rational number. So now the question is, can I write square root 2 as some number right here, some fractional number that I could then convert into some P over Q? And how would you answer that question?
No, you can't.
Why not?
Say we could write it as the ratio of two integers in its simplest form.
Okay. Okay, so Rhyme, I'm about to stop you just right here because we're going into the proof, and I want to know if anybody else has any comment before we go into the proof. What does everyone else think about us writing square root of 2 as some number, which I can then write as P over Q? By the way, if you're worried about infinitely many numbers, that's not a problem, because if you think about 1 over 3, what's the decimal representation of 1 over 3?
0.3 recurrent.
0.3333 keeps going on. It's a recurring fractional number, which we denote as 0.3 with a bar on top, which basically just means the same thing, but it's still a rational number. So just the fact that we run into lots of numbers and we'll keep zooming in, that's not really a problem, because you can get, perhaps we might be able to get a pattern somewhere. Okay. Does anybody else have a comment before we dive into the proof?
You mentioned
under root 2,
that,
I mean, is it again, sorry.
Go on.
Yeah, so is it again a recurring number? Because whenever we put this number into the calculator, it gives us just like, 10, like after decimal, the 10 or 12 digits which comes. When you square it, it gives you 2 itself. So is it,
Yeah.
I mean, when we can't actually do it with your, manually, we can't do it. So is it
so when
a
you say you
number
square it,
never ends?
So I just have a question. When you say you square it and gives you 2, are you squaring it on the calculator or are you squaring it yourself?
Yeah. No, I'm squaring it on the calculator.
And it gives you 2?
The number which, yeah, it gives me 2, yes.
Okay, and what number is that?
So it's 1.4142135624.
5624. And here is a little exercise for anyone who's has the time after the class. Take this number and instead of multiplying it on your calculator, do it yourself. 1.4121355624. If this is indeed exactly square root of 2, when you do this multiplication, you should get 2.00000000000.
We won't, sir.
You won't. Why not?
This won't be perfect.
Sir, is it,
On the calculator, it shows us the rounded off version. It doesn't show us 2.0000.
Yeah, it's an approximation. So when
It will
you
be
input
precisely
square root of 2 on the
accurately.
calculator, it's actually basically done as much as it could, as much as it was, or more than as it could, as much as it was programmed to do. So whoever programmed the calculator said, okay, these many digits are enough. You don't need to go further. But this number, when I write the equals to sign, that's absolutely wrong. Because this is actually just an approximation. Because they've stopped. Just like 22/7 is an approximation to pi, it's not exactly equal to pi. Same, square root of 2, with what the number that calculator gives you is an approximation. It's stopped. It's sort of been lazy and just stopped.
That's what I mean, that it's a recurring number, right? Never ends. Under root 2, it never ends.
Okay, so there's a difference between recurring and then non-terminating. Okay, so we say that a number terminates if after some point you start getting 0, 0. So that's a terminating number, right? A non-terminating number could be that it keeps going on, but perhaps it repeats some pattern. So let's say 6 to 4, and it starts repeating this pattern over and over. So it starts repeating 6 to 4, and then it starts going from that, and then this pattern keeps repeating itself, 6 to 4 and 6 to 4 and so on. Now that is a recurring non-terminating number, right? So this is a recurring number. Now the nice thing about recurring numbers is even recurring numbers can be written down as P over Q. Just like we saw in 1/3, it's recurring, 0.3333, but it still can be expressed as 1/3. The only problem arises when it's non-recurring and non-terminating. So it's, let me write that down, non-recurring and non-terminating.
sir?
Yeah.
Sir, aren't we essentially like describing what an irrational number is by saying they're non-recurring and non-terminating?
Yes and no. Yes, in the sense that it turns out to be the case that irrational numbers have these properties, but no, in the sense that I don't really have an example of such a number yet, and I need to see such numbers exist. And the whole point of doing this exercise is to show that actually square root of 2 is one of these numbers. It's a non-recurring, non-terminating number which cannot be written. And rather than saying that it's a non-recurring, non-terminating number, a better definition would be that it cannot be written as P over Q. That you can't have two integers that you write P over Q and it gives you square root of 2. Okay. All right, so those are good comments. And now let's Ryan take it away.
Say we could write square root of 2 as P over Q, where P and Q are coprime.
Okay, where P and Q are coprime. And now for the benefit of everyone here, why do you need this statement?
Because later a contradiction will happen where these where P and Q will have a common factor, but otherwise it's because any fraction can be written in a simplest form.
Okay, so I'm going to add a fact here that any fraction, which is a bit more accessible statement, can be written as, can be reduced down, can be reduced to its simplest form. So for example, suppose you have 33/11. Of course, it's a rational number, but it's not in its reduced form. Its reduced form, once you take out all the factors and cut them away, its reduced form would be 1/3, so 3/1. So it's just the number 3, right? If you have, let's say, 49/21, it's again a rational number, but it's equivalent to another rational number, which is just 7/3. So what we're encapsulating in this statement right here is that whatever fraction it is, whatever square root 2 is, we're going to reduce it down to its simplest form. So P over Q is basically the reduced form. That's what we're assuming, that we want the reduced fractional form. Is everyone okay with that statement?
Yes, sir.
Any issues, any questions in that statement? Feel free to ask, because that if you lose it at any point, then you'll have trouble following the rest of the proof.
Should I carry on?
Sure, go ahead.
So square root of 2 equals P over Q. So 2 equals P squared over Q squared.
All right, so now what we're doing is we're squaring both sides, and we get 2 equals P squared over Q squared, okay?
So P squared equals 2Q squared.
P squared equals 2Q squared.
This must mean that P squared is even.
All right, so now we're making a logical claim. We're saying this means that P square is an even number. Can anyone other than Rhyme tell me why does this statement tell us that P square is an even number?
Because it will be a multiple of 2.
It's a multiple of 2. Any number that's a multiple of 2 has a factor of 2. You can divide it by 2. That means, because even numbers are known as the numbers that you can divide by 2, right? Okay, so all right, now what?
If the square of a number is even, then the number must be even.
All right, now if the square of a number is even, then the number must be even. And why is that?
Let's say we have an even number. It can be written in the form 2m. If we square that, we have 4m squared, and that's a multiple of 2.
Okay, all right. Okay, so I'm going to actually leave this as an exercise, and I want you all to try this. We're going to leave it as a fact because I'm just going to see a few examples and just take it as a fact. But I want you to do this to get a feel for how you would prove a mathematical statement. But let's see a few examples. So for example, if I do 2 squared, that's 4. So an even number gave me an even number. If I do 3 squared, gives me 9. So an odd number gave me an odd number. 4 squared gives me 16. Even number squared gives me an even number. 5 squared equals to 25, odd squared gives me odd. So it sort of seems that if you keep going on, what Ryan just claimed here seems to be right. Okay, so let's take it as a fact then, because it seems like this is going to go on. Okay, so what does that give you, Ryan?
So P is even.
So now you claim that P is even.
So P can be written as 2K.
All right, so P can now, I'm going to take this stuff and take it away. Oops, that period came at it, but that's fine. Okay, so P can now be written as what?
As 2K, where K is another integer.
Where K is just an integer. Okay.
If we
All right.
substitute this back, we get 2K whole squared.
Okay, 2K whole squared equals
4K squared,
4K squared. Okay.
which equals 2Q squared.
So we already have that P squared should equal this. So all we're doing is we're substituting 2K in this equation and we have 2Q squared. So I get that 4K squared equals 2Q squared. Okay.
So Q squared equals 2K squared.
So now I can make that claim. So if I divide the whole thing by 2, I have 2K squared equals Q squared.
So Q squared is even, since it's
All
2
right.
times another integer.
So Q squared is now even. Okay.
So Q must be even.
All right, and now we're going back to the same statement that we had before, which is if the square of a number is even, then the number must be even. So the same thing that we used for P squared to show that P is even, we're now using for Q squared. So this gives me that Q is even as well. Okay.
If both Q and P are even, then they must have a common factor of 2.
All right, so these are the important statements. Now we know that P is even, and we've just concluded that Q is also even. So now, combining these two facts, I have the fact that since both are even, then they have a common factor of 2. Okay.
This means that P over Q can be reduced, which contradicts.
Therefore, yes, so P over Q, which initially is the reduced form, turns out it's not really reduced because we said we can write P as something like 2K. And since Q is even, I could write it something as 2M because both are even. This is an even number. This is an even number. So it must be a multiple of 2. And I can cancel out the 2's. And I get a number which is K over M. So if P over Q is not the reduced form, then our initial assumption is false. So what does that tell me?
This means that the square root of 2 can't be written as a reduced fraction. And since any fraction can be written as a reduced fraction, square root of 2 can't be written as a fraction. So square root of 2 can't be rational.
Okay, so does anybody have an issue with this statement? Square root of 2 cannot be written in a reduced form.
Sir,
G.
do we imply that like if it cannot be written in a reduced form, the process of reducing it will basically continue, right? Because our initial assumption is that P over Q is a reduced form, right?
Exactly, right? So the train doesn't stop because if after this whole proof you say, okay, maybe K over M is the reduced form that we were looking for. What's the problem with K over M then? Why can't I just say square root of 2 is K over M and be done with it?
Because then you'll just go onto the whole process again.
Yeah, because then I just, whatever I did with P over Q, this whole squaring and then this whole argument that we just went through, I can do the same thing for K over M. So if I make a line here, I can say by the same argument, K over M, just like P over Q were written as the multiples of 2 of something else, then I could write maybe K over M as, let's say, 2 times L divided by 2 times N. And now I have a new reduced form. So it doesn't look like I'll ever be able to find a reduced form because the factors of 2 just keep turning up. So this is the important problem. The important problem is this can't be reduced, square root of 2 can't be written in reduced form, but every rational number can be. Every rational number can be written in reduced form. And of course, this is something that I'm taking for granted. I haven't proved this. So maybe you can think about it and maybe you can come up with a mathematical argument that proves this statement, that every rational number can be written in reduced form. So I'm going to leave this as an exercise and I'm going to leave this also as an exercise. So just to be clear that these examples don't constitute a proof because these are just 5 numbers that I've checked, but maybe the pattern breaks down somewhere. So just because I've checked 3-4 numbers doesn't mean the pattern will continue. I mean, even if I write 6 squared and 7 squared, I know this is 36, so even gives even, and 7 squared is 49, so odd gives odd. Just because the square of a number is even doesn't mean the number itself must be even. So this is, let me just say that this part, finite number of examples are not a proof. Okay, because I haven't checked all the numbers, and of course I can't. All right, so this is perhaps the classical example of a proof. What we just did was a proof by contradiction. Okay, it was at the core of it, there were a few mathematical arguments, and you can sort of see that we sort of built upon some previous facts. So the facts that I used were, this was one fact, or rather I'm used, which was this fact, which needs to be proven. And once we prove that fact, it will be part of the structure. So you can think about this square root of 2 is irrational, is sort of built upon these other 2 structures, right? One of which is that if p square even, then p even, that's one statement. And the other was every fraction can be reduced. And perhaps these statements are also built upon, once you prove these statements, these are built upon some other statements. Okay, these statements might be built upon some other statements. And so once you reduce it down to statements that you're sort of sure of, then you have a good structure for one statement, which is that square root of 2 is indeed an irrational statement. And then you can be convinced that actually there is no such p. So let me write, it does not exist. It is not the case that there exists p and q such that square root 2 equals p over q and let's see, and p belongs to the integers. So p q belongs to integers and q is not 0. Okay. So all I've said here is that this statement asserts that square root 2 is rational, and I've put in a negation. So this symbol indicates a negation. This symbol indicates there exists PQ, such that square root of 2 can be written as P over Q. And this is just simply a shorthand for AND, okay? The conjunction operator. This is AND, okay? Any questions?
You just said that every proof is based upon another proof, right? So
Yeah.
what is the most basic of proofs, like on which every other proof is based on?
Interesting
If
question.
that is something, like if it exists, that is.
Great question. And again, it brings me back to the earlier conversation, which is first you would, if square root 2 is irrational, at some point in this structure, you would end up with the questions of what's a real number? And then you need to construct the real numbers. So construction of real numbers, and then once you have a structure that resembles the set of real numbers, then maybe you can build upon these facts on that. Because all of this is based on, so if you're talking about even numbers, well, once you have even numbers, you may need to define what even numbers are. You may need to define what fractions are. So at the most basic level, there will be some axioms and there will be some definitions, and there will be some rules from which you can go further, right? So it's question is, you keep asking why, and you follow the rabbit hole as far down as you can make it.
Sir?
Yeah.
Sir, can you please go over how this is a proof by contradiction? I think I missed that part.
Okay, so it's a proof by contradiction. What's a proof by contradiction? So a proof by contradiction is that you assert that P is true, okay? And then you logically conclude that the negation of P is also true. So for example, if I say that, something, I don't know. So if I make a statement and I assert that it's true, and by following just simple logical rules, I end up with the fact that not P is also true. So for example, let's say Earth is flat. That's a logical proposition that I'm making. And then, or actually, you know what? Let's make a statement. So let's just show how this is illustrated in the example that we just did. So what we just did is the statement that I asserted to be true is that I asserted that square root 2 can be written in reduced form. So my statement, my proposition was that square root of 2 can be written in reduced form. Okay, it's a rational number.
And you proved the opposite of that through logical reduction.
Exactly. Right? And so logically, I deduced that actually square root 2 cannot be written in reduced form. Right. So what I've essentially said is, on one hand, I said P is true, and on the other hand, I said not P is also true, which is a contradiction. So this and this combined together. So something in mathematics in simple notation, what we write is that this is a contradiction, P and not P. This is called a contradiction because this statement is always false. you can never have both these statements being true at the same time, right? Okay, so
Yes, sir, thank you.
the contradiction that we derived was at this point, right? This was not P. Okay, and I noticed that there are two P's here. One of the P's was P over Q. The other P stands for proposition. So let me just write this as PR. So you know that this P stands for the proposition that it can be written down. So let's call this PR. Okay. So that's how it's a proof by contradiction. And so what is a proof? A proof is simply a set of logical deductions that you make. We can actually boil this down. If we were to use mathematical language at every point, then I could perhaps write it something like this. Let square root of 2 equals P over Q. And then I just write 2 equals to P squared over Q squared. 2Q squared equals to P squared. P squared even, P even, and then 2Q squared equals to 2K squared, and then Q squared equals to, so 2, okay, so I'll get a 4K squared here and a 2Q squared here. So Q squared equals to 2K squared, Q squared even, Q even, and therefore P over Q equals to 2 K over 2M, and I could actually put just a full stop there. So I've actually made it more verbose than it actually needs to be. I could even skip these statements, right? I could just skip these statements, and this is one of the things that happens when you read somebody else's mathematical arguments, is that sometimes they would skip steps that would seem very obvious, right? When I go from this step to this step, for me, it's very logical. Somebody else reading my work would be questioning why was P written as 2K? Whereas to me, it's obvious. P equals to 2K just means it's an even number, and I've assumed it from this. So you sort of have to, sometimes when you're reading mathematical books or text, you have to fill in the blanks about what logical deduction takes us from this step to this step. Okay.
Sir, I had a question, and that was,
Yep.
Is it necessary for the number to be positive? Because even if it's negative, then the square would yield a positive result. Even if it's a negative fraction, like both like P and Q are negative, then still it would yield a positive value. So like why
Which
is
number needs to be positive? P, Q, square root 2? Which
like you
number are you
stated
talking
that,
about?
P is even and Q is even, so that's not necessary. We can also say P is negative, and then Q is negative, then P squared would yield a positive value. Q squared would yield a positive value. Like if we say it's like 4 upon 9, we can also write it 2 squared upon 3 squared. We can also write it negative 2 squared upon negative 3 squared. And both of them would give the same answer. However, the initial fraction is like the initial numbers are 2 and negative 2, 3, or negative 3.
Okay, so your question is, what if P and Q were both negative, right?
Exactly.
But at what point did I claim that P and Q were positive?
P and Q need to be negative because otherwise you could cancel out the negative signs and it wouldn't be in reduced form then.
All right, so if P and Q were both negative, then P over Q are actually, let's write them down as negative P prime, and P prime is some other number. Maybe let's just use some other, negative R over negative Z. Okay, if they're both negative, then what's the issue with that? And Ryan just pointed it out, it's not in its reduced form. It's just -1 times R divided by -1 times Z, and you can cancel out the negative. So if it is in reduced form, reduced forms are always, we've discovered another fact, reduced forms are always positive.
Not if one is positive and one is negative.
Yeah.
Well, yeah, okay, fine. At least in this case, it's positive. If one is, what's the issue? Okay, fine. So
And
what's the issue? How can we rule out? So what if 1 is negative?
Because square root of 2 is positive, it needs to be written as a positive fraction.
Exactly. So now the problem is we already have a sense of what square root 2 is. It's between 1 and 2. So either both the numbers are positive or either both the numbers are negative. I've already ruled out that both the numbers can't be negative because then it's not in reduced form. So the only possibility really that I have left is that both of them are positive. Does that make sense?
So, but like like it kind of take us to the path that we are convincing us or forcing us to say that square root of 2 cannot lie between -1 and -2.
I'm actually definitely making the claim that square root of 2 cannot lie between -1 and -2. And can somebody give us a good reason for why I think that square root of 2? Okay, so question, what if square root of 2 is a negative number? So can someone explore this possibility and tell us why this may not be the case?
The square root sign is talking about the positive square root. If I talk about the negative square root, I need to put a negative sign before that. But both are irrational.
Okay. So one thing,
sir,
there's a difference
can I say
between,
something?
yeah.
Sir, say if we put a negative sign in front of root 2, or let's take another example. We take a root of -4. But even if we square -2, it gives us +4.
Okay.
Because minus and minus gives us a positive.
Yeah. So there's a difference between putting a symbol and then understanding what that entity itself is. There's nothing that I know about this number other than that I've just written it like this. Even if I wrote it like positive square root 2, it doesn't really add anything to my understanding of it. And the reason why it doesn't add anything to my understanding is because I don't know what this number is. I've only deduced a few things about this number, which are that it should exist. And if I take you back to that argument about if it existing, let me take you back to the geometrical argument that sort of compelled us to believe that it exists. I drew this rectangle. It has a length of 1 and a length of 1. It has this length. Now, I have trouble believing that the length of this triangle is a negative number. Because in my worldview, having negative length is problematic. Because so far I haven't defined any direction, right? When you put in a negative sign, you're basically talking about the direction of the length. But right now it's just a length. It seems positive to me, definitely. And it seems that if I have a length of 1 and I have a length of, let's multiply this and let's get a bigger length of 2. And if I take this one and put it somewhere here, right? Why should this be a negative entity? So that's one thing that compels me to think that this is indeed a positive number. The other thing that compels me to believe that it is a positive number is to go back to that argument that I was trying to make, that, it seems like I stay between this range of 1 and 2, and I start finding this number, and I start finding this number, zooming in closer and closer. Now, if I were to multiply whatever this number was whatever this number is, this x equals to square root 2. If I were to multiply that number by -1, so if I now say I'm looking at -1 times x, then by our understanding of mathematics, or at least the real numbers, is that I would get the mirror image of this number right here. And so, sure, it's the same number just with a negative sign attached to it, which means I'm interested. So let me say I'm interested in the magnitude. Not the direction, sort of, because I'm just looking for this length of this triangle that's so simple to make 1, 1 and square root 2. I'm just interested in the magnitude of that length. And now if I draw that same magnitude on the other side, sure, that's negative square root 2, and the other one is square root 2. Now, if you were to say that, you know what, maybe that number is the negative number. So if you choose to call this number as the square root of 2, then you will have to call this number on the other side of it as the negative square root of 2. It makes absolutely no difference to the magnitude. So by convention, I'm saying the right side is positive, the left side is negative. It's still the same length. Does that make sense?
Yes.
Or maybe, I don't know, maybe somebody has a better insight than that to share.
So I guess it's better to say that irrespective of the direction or the sign, we are just focusing on the magnitude itself. Because
yeah, I'm just talking about the, yeah. Perfect. Like if let's suppose you say, what if square root 2 is a negative number? Okay, fine, square root 2 is negative x. I want to simplify my things. I want to get rid of this negative x. Actually, you know what? You do the same argument with p over q. Argument still follows. One of them is negative, one of them is positive. You still find the factor of 2. So whether it's positive or negative makes absolutely no difference to the fact that it's an irrational number.
Perfect, sir.
Right.
Though this was an amazing argument, sort of, because like the discussion between us, that was amazing. Like okay, it could be positive or negative.
Right. I'm glad you. It sort of makes you question your ideas about these very basic numbers that you've sort of been working with mindlessly for quite some time now. Yeah, I'm glad that was insightful to you.
Sir, I have a question.
Mm-hmm.
When we square root a number, your answer always ends up being either positive or negative, right? Because for example, if it's under root 4, your answer will be plus minus 2.
No, absolutely not.
What?
Okay, so here's something that we often, I think it's a problem of teaching this stuff, and I've made the same mistake myself. When you square root something, don't you get both positive and negative? And that's really the wrong way of remembering what this is. So let me tell you what the fact really is and how we end up, misusing that fact. So suppose I were to say that x squared equals to 4. I give you an equation. Okay. If I were to give you this equation, x squared equals to 4, and I said square root both sides, well, you square root this, square root x squared equals to square root 4, and now you write x equals 2. That's half the truth. Because what you've just missed out is that even if you had negative 2 and then you squared it, that also gives you 4, which means there are 2 answers to this equation. So basically you were solving an equation And so whenever, and this is something that we teach in our college algebra course, is that if you want to solve the equation x squared equals to a, the solution to that is x equals plus minus square root of a. Okay? There's a difference between solving an equation and then talking about just the entity square root 4. Well, square root of 4 is just 2 because by not writing anything, I've assumed that there's a positive sign. So the right way of doing this is whenever you square root two sides, you put a plus minus on the right hand side to account for the two possibilities that square roots sort of come in pairs. So the right thing to do here would be x equals to plus minus 2. So when you solve an equation, you say x squared equals a, then you say, okay, there's two possible solutions to x, either positive square root of a or negative square root of a. But when you just talk about square root 4, that's just 2. When you just talk about negative 4, then that's just negative 2. Does that make sense?
Multiplying two negative numbers give you a positive result?
Sorry, say that again.
When you multiply two negative numbers, your result is positive, right?
Yeah.
So if I have a negative sign before the square root of 4, my result won't be negative 2. It will be.
But where in this whole thing am I multiplying two negative numbers? I'm just saying negative of square root of 4, and I've already know that square root of 4 itself is just 2.
Oh, okay, I get it now. I think that's what I was having confusion.
Yeah, we often, several of my students have also made this mistake, and I think I at some point also had this confusion, which was that when you solve the equation, that's when you account for the two possibilities. Yes, Dr. Danish, you want to add in to that?
Yes, I want to add one thing here. The definition of this square root of x square. The square root of x square is always equals to absolute value of x. Okay, this is very important thing which students miss this thing. That is why because whenever you have the square root of x, the absolute value of x is that its definition is that it is equals to x when x is greater or equals to 0, and it is minus x when x is less than 0. So so this is the thing which must remember.
Did I also make this mistake here? Let me just check my working. Okay, so right, so this is so what I should have done, I've made a notational mistake. What I should have done, I should have just written x equals to plus minus square root 4. Right, so when you write square root x squared, that's actually the definition of the absolute value of x, which makes sense because on the right hand side, this is always a positive number, right? So inside this is a positive number. Is that fine?
Yes, yes, it is fine. Just you have be careful about this thing. So students actually miss this concept.
Yeah, I also sometimes in notation I end up making this mistake as well, and then it turns out that this is an interesting thing that I think also turns up when you try to prove the quadratic formula, and we sort
because
of
when you're taking the square root of 4, this is always equals to 2. This is not, because whenever you are taking the square root, this means the positive square root. Okay.
Yeah.
So but you are solving, when you are solving this equation, x square is equals to 4. So actually it means that we are finding all those real numbers whose square is equals to 4. So the negative number square is also positive number. So negative 2 and positive 2 both are the solutions of this.
Yeah, you're looking for any possible x that satisfies this equation. So if you just go on and do mindlessly just say x equals to 2, then you've actually not solved the equation completely. You've missed out on one of the solutions. Okay. All right. So I think we're out of time. I think I've gone slow. I've wanted to cover a couple more proofs. I don't think we have the time. Does anyone have any questions, any comments about this? Anything that was unclear?
How can we do this with other irrational numbers?
Okay, so question, how can we do this with other irrationals? First, I want to ask the question, what do you mean by other irrational? Which exactly irrational numbers are you talking about?
I'm not talking about e or pi. I'm talking about things like the square root of 3. Oh.
Okay, so how would you carry over this proof for square root of 2? How would you prove? Question, how would you prove square root 3 is irrational? Do you think we can pull off the same proof?
No, because we'll get p squared equals 3q squared. And we don't know if that's even or odd.
Right, so that doesn't seem to work there. All right, so there's square root 3. And let's look at the pattern here. So square root.
It is multiple of 3, maybe, right? Because even is a multiple of 2.
Yes.
So then you would need some fact about multiples of 3.
But they can be odd or even. 6 can be even, 9 is odd, 12 is even.
Right, so it's then you will have some cases to look at. So if suppose, then you'll have to go through each of these cases. Now suppose p is even, what can you conclude about it? Maybe it might give you an insight into it. So this can definitely be done, but you have, it's not as elegant as the proof of square root of 2 is irrational.
I think 3 times an odd number is an odd number, and 3 times an even number is an even number. And then we would have to do case 1, q squared is even. And yeah, I think.
So you don't know whether q squared is even or odd.
Yeah.
So then maybe you go into each of these cases individually. So assume q squared is even. What does that tell you? Assume q squared is odd. What does that tell you?
If it's true that 3 times an even is an even.
Which seems like it's true. Any odd number times an even number. I don't see why it shouldn't give me an even number.
Yeah, so if q squared is even, both q and p are even. So there's a common factor of 2.
P squared is even, and then p is even. So now we have p is even, which is, so p is 2k, and q already we established because q squared was even.
If q squared is odd, then p squared is also odd, but that doesn't mean that they have a common factor.
All right, so if q squared is odd, then p squared is also odd. Okay, then what can you do with it? So let's say p squared equals 3q squared.
Q equals 2k plus 1. No.
Q equals 2k plus 1. Yeah, sure, why not? And p equals what? If q squared is odd, then does that necessarily mean that q is odd?
Gautam, if I can make a statement, for example, if here p square is a multiple of 3, why not you say, if I write a statement, if p square is a multiple of 3, then p is also a multiple of 3.
Okay, so if p square is a multiple of 3, p is also a multiple of 3. And why should we believe that statement?
You believe that p square is even, then p is also even by taking some examples. Okay, so at the moment you do like this.
All right. So at the moment we'll just take it, but we'll leave it as an exercise for you to, for other students to explore this further. Okay. So then
p is multiple of 3, then p is equals to 3 times some k, and if it proceeds like this, I think then you can also show that q is also a multiple of 3, and then you get a contradiction that both have a common multiple.
That's absolutely true. If this statement holds, then if the similar statement for even numbers holds for this multiple of 3 kind of situation, then we have exactly the same kind of proof, and then it should follow. So let's leave it as an exercise for them to explore on their own. Let's see if they can finish off, or maybe they can go down this rabbit hole and see if they find something interesting here. And actually, it's an interesting exercise which geometrically, even the other day when I was preparing for this one, it was a delight to make up these triangles. So 1, 1, and square root 2. And now, why should you believe in square root of 3? Well, let's make a side of length 1 at 90 degrees right here, and then join these. So if this length is 1 and this length is square root 2, what does this tell me about this length?
Square root of 3?
That's the square root of 3, because it's going to be some side c squared, which is equals to 1 squared plus square root 2 squared, which is just 1 plus 2, which is 3. So I have c squared as 3. That means here I have square root 3. And now you do the same thing and you draw a line here at 90 degrees and then you join the length. What do you get?
4, square root of 4.
Square root of 4, which is now suddenly after 2 irrational numbers, you have a rational number. And then you go on and you make these lengths, and these lengths start getting longer and longer, and you start getting square root of 5. And you actually end up with something called it's not a triangle, it's more like what it's be, and it's called the spiral of square roots. It's an interesting geometric exercise to do, and you end up getting lengths. All these lengths are 1. This is 1, this is 1, this is also 1. But these hypotenuse, they start increasing, square root 5, square root 6, and then you get 3 of these, square root 6, square root 7, square root 8, and then suddenly you have another rational number 3. That's an interesting pattern that you can look at. All right, I think that's all I want to say here.
I want, Gautam, one more comment about this, what you have given as an exercise. So if we generalize this thing, as somebody mentioned that, or asked that, what about the other rationals, like square root 3, square root 5, and square root 7, and square root 6? We know that whenever there is not a perfect, a number is not a perfect square, then its square root is a rational number. So if we generalize this statement and try to prove this statement, that if p square is a multiple of k, where k is not a perfect square, then p is also a multiple of k. So if this is true, then this general statement will prove for all numbers of type square root of k as an irrational number. Here k is not a perfect square. Multiple of k,
not a perfect square.
Yeah. So this gives you the
so you can
irrational number of the form square root of k.
Right. So from square root of 2, you will, sorry, I forgot. There's a 3 here. So there's a 2 here, then there was square root of 2, and the square root of 4, square root of 3, square root of 2, and there's a 1 here. Yes, so I would say, yeah, you should explore this, and this is a step-by-step process that you can do. You do it for square root 3, you prove the statement, and then it almost falls out like it is the same proof with exactly the same statement. All you will need to do is prove this general statement. So it's an interesting exercise for you all to do.
Or give an example which dissatisfies this statement.
Sorry?
Or they can give an example which dissatisfies this statement, which means that this generally this statement does not hold, and then we need to have some other proof of showing the square root of some non-square number is a rational number.
Right. So Dr. Damis just highlighted an important principle that if you want to disprove it, all you need is just one example where this statement doesn't work. If you have just one counter example, then you don't need it. You don't need to do anything else. Disproving is really easy if you have the right counter example. Proving, however, is a difficult task because you have to generalize it for all statements. Okay. Let's stop here then. Any questions, comments, statements? Sorry, we went here 15 minutes further. All right, if there's no, is this relatable to polar coordinates? I'm not sure how you would think that. Maybe because I was drawing it like, oh, if you were looking at the spiral and thinking, but I don't think so now. I mean, you could look at it, but I'm not sure I see a direct connection with polar coordinates there. Okay. But he said about growth, the next thing he says will be that. Okay. All right. Thank you, everyone.